I now want to talk about integral transforms. Okay, these essentially come in different forms. There are different types of integral transforms that you can possibly encounter. The most popular ones are the Fourier transform and the Laplace transform, which I'll be talking about. But there's some others as well: the Henkel transform, the Hilbert transform. Okay, essentially the idea is this: you have some problem that you want to solve. Okay, so you can solve it directly. Okay, direct approach, you'll arrive at the solution, but this direct approach may be difficult. So for example, if you want to analyze some problem involving a function that is dependent on time, you might be trying to attack that problem directly. Okay, another alternative is that you change the space of the problem, okay, by doing an integral transform. You understand what I mean by this when we come to when I demonstrate to you, for example, the Fourier transform or the Laplace transform. You change your space. So for example, if you had a function that was dependent on time, instead of looking at the time dependence of your problem, you will look at the frequency dependence of your problem. Okay, and then you have this modified problem in this new space, and then you can solve this modified problem with your easiest modified problem in this new space, and then of course you can then reach the solution. Okay, this might be an easier approach. Okay, so for example, if you have a differential equation, as you'll see, okay, solving it directly might be difficult. Okay, but if you have an ordinary differential equation, if you then take a Laplace transform, your differential equation reduces to an algebraic equation. Okay, and we know how to solve those. Okay, you have a quadratic equation, you know how to solve it. You have a linear equation, you know how to solve that. And then once you have the solution to your this new algebraic problem, you then translate the solution back to your actual physical space. Okay, the original space. Similarly, if you have a partial differential equation, it might be useful if you take a Fourier transform, for example. Okay, and then you can convert many problems involving partial differential equations to problems involving ordinary differential equations. Okay, and we know how to solve ordinary differential equations. Okay, so that's basically the idea. Okay, so before going on, let me just make this clearer because I skipped one step away. Okay, so you have modified problem, you have your solution in new space. Okay, and then you translate this back to the solution in the original space. Okay, right. So for example, if you had a function you had which varied with time, you were dealing with the time dependence of the problem, you convert your problem to looking at the frequencies. You solve this in the so-called frequency space or frequency domain, and then this new solution you convert it back to what does it translate back to your original time domain. Okay, the prototypical example of this integral transform is given by the Fourier transform. Okay, and we should be comfortable with the Fourier transform because a lot of it builds up on what we have learned previously regarding Fourier series. Remember, for Fourier series, let me just recap. For Fourier series, you had to have a periodic function. Okay, or you needed to make it periodic. Okay, but suppose you have a function defined from minus infinity to plus infinity. Okay, and you should then have to write down some kind of series expansion for that function. Okay, in terms of complex exponentials. Okay, so if your function was periodic, remember you could write this down: Cn e raised to power I n pi x over L, right, where L is the period of your function. Okay, and these coefficients are given by this thing. Okay, so you integrate over one period your function, and you have over here e raised to minus I n pi x over L. Okay, now in our case, if you are dealing with a function which which is defined from minus infinity to plus infinity, which is not periodic, okay, in general, you want to do something similar with such a function. Okay, now we can do something similar if we recognize that for such a function the period itself is infinity. Okay, so in other words, we can loosely speaking, we can take the limit of the Fourier series for the case where the period goes to infinity. What happens when you go from a finite period to an infinite period is that these Cn's, instead of having a discrete set of these complex coefficients in your Fourier series expansion, you have a continuous set of them. Okay, so this sum becomes an integral. Okay, so your f of x, rather than being expressed as sum, is expressed as an integral. Okay, so that's the key idea behind you expressing some function as an integral, okay, as a Fourier transform. Okay, okay, so let's see how that happens. Before we do that, I have to essentially take the limit of this whole thing when L approaches infinity. To do that, let me just clean up some of my notation. So n goes from minus infinity to plus infinity. Cn e raised to power I k n x. So k subscript n is defined as n pi over L. Okay, so you can see that these k n's, okay, for finite L form a discrete set. So if n is 0, of course, then k is 0. N is 1, then you get pi over L. N is 2, you get 2 pi over L. 3 pi over L, and so on and so forth. Similarly, you get minus pi over L, minus 2 pi over L, and so on. Okay, and you can see immediately that when L approaches infinity, the spacing between these different points, okay, the spacing between these different points in the so-called K space becomes smaller and smaller and smaller, until when you really do reach the limit when L goes to infinity, these actually form a continuum. Okay, so that's what I meant with it. This sum will go to become integral, because this sum is over the different values of k, and when k itself, instead of forming a discrete set of values, it itself becomes a continuum, then this sum becomes an integral. Okay, right? So just to then make the fact that this sum becomes a continuum clearer, let me just rewrite this sum as in the following form, that sum over n correspond to sum over the allowed values of k. Okay, because this sum over here I'll be converting to integral over k. That's why I'm doing this change of notation. C depends on n. If it depends on n, then of course, because of this relation, depends on k. So I'll be writing c k n. Okay, or just to show that C depends on Kn, probably a neat notation is this, and you have this. Okay, we also have that C Kn is given by 1 over 2L minus 2L L dx f of x. That, okay, until now just a nifty change in notation. Okay, and now I just want to convert this sum to an integral. Okay, so what I'll do over here is the following. Okay, I need to convert this sum to an integral. Okay, and this is a trick that is used over and over again in different areas of physics and engineering. Okay, so I have these different values of k, like I identified over here: 0, pi over L, 2 pi over L, 3 pi over L. I can write down the spacing between any 2 points is of course given by pi over L. Okay, then from this relation I can write down that L delta k over pi is equal to 1. Okay, I am doing this because of course to convert this sum to an integral over k, I need to have delta k appearing somewhere. So then this sum I replace by integral sign, and delta k I replace by dk. Okay, now since this is an identity, I can insert over here kn c kn e raised to power I k n x L delta k over pi. Okay, right. And then I can write this thing down as sum over kn, and then for ckn I replace this thing. So I have 1 over 2l minus l 2l f of x e raised to minus I k n x, right, e raised to power k n x dx, okay, e raised to power I k n x L delta k over pi. Now I have to be a bit careful about the notation over here. X is of course some point that I'm already talking about, the value of the function f at the point x, okay. This x over here is different, okay, because this is essentially the dummy summation variable in the integral, because remember the integral is also a sum, okay. So just to, so that I don't confuse this x with this x, let me just put a prime over here, okay. Okay, this x is the same as that x, so that's fine, okay. Now this L over here cancels this L, okay, so then I'm left with summation over kn, okay, and I'm left with 1 over 2 pi, okay, so this pi over here, this pi I take inside, so 1 over 2 pi, and then you have minus L over 2L f of x prime e raised to minus I k n x prime dx prime, okay, and then I have e raised to power I k n x delta k, okay, and now I take the limit that L goes to infinity, okay. When L goes to infinity, this sum over discrete values of k becomes a sum over continuum values of k. So I replace this with the integral, okay. The values of k, looking at this range, will range from minus infinity all the way there to plus infinity all the way there, okay. So my integration limits are minus infinity plus infinity. This delta k becomes dk, and then I have this 2 pi, so I have dk over 2 pi, okay, right, and then I have e raised to power I k x, this vector, right, and then I have this thing minus L to L f of x prime e raised to power minus I k x prime. Oh sorry, I should be integrating from minus infinity to plus infinity, because I'm already taking the limit that L goes to infinity, and you have this, right, okay. So this is the so-called Fourier integral theorem. Okay, this relates the integral of f of x to the original function. Just to see that clearly, let me define a new notation, okay. Let me define for example, let me define f of k as this thing, okay, f of x e raised to minus I k x dx. Well, I'm not putting prime because of course the integral over here is over x, okay. It could be over x prime, it could be anything. The result will be a function of k, okay. It will be the same function of k, okay, because you have in the integral from minus infinity to plus infinity, okay. It doesn't matter what you use for the variable over here. You can use y, you can use x, you can use z, you can use x prime. You will have the same capital F of k in either case, okay. Capital F of k is a function of k, of course, is called the Fourier transform of f of x, okay. Then this integral theorem says that the original function f of x is given by minus infinity to infinity dk over 2 pi e raised to power I k x, that, okay. So if you want to get the original function from the Fourier transform, you plug the Fourier transform into this relation, multiply this by complex exponential, and then do the integral, okay, and you'll get back the original function. So this is a two-way street. You can go from the original function, take the Fourier transform, okay, and you'll get capital F of k. That's the Fourier transform of f of x. Okay, so Fourier transform, you end up with f of k. Okay, and you can go backwards. Okay, you can take the inverse Fourier transform if you want to say it like that, and you'll get back to f of x. Okay, that's how you get back to f of x from capital F of k. This is how you take the Fourier transform. Okay, now one thing that I should make clear is that if you go back to the Fourier integral theorem, this one, okay, so let me just rewrite that. F of x is equal to minus infinity to t dk over 2 pi dx, and then we have e raised to power minus ik x f of x. It should be prime over here, right? Okay, and then I have e raised to power ik x, and that's it. Okay, so one thing that I should make clear over here is that there are different ways that you can use this to define the Fourier transform. Okay, I've done it in one particular way. There are other ways as well. In different books you see the Fourier transform and the inverse Fourier transform then defined in different ways. Okay, so for example, some people say that, okay, let me define k prime is equal to as minus k. Okay, and then of course dk prime is equal to minus dk, and you can then write the Fourier integral theorem as, well, when k is minus infinity, k prime is plus infinity. When k is plus infinity, k prime is minus infinity. So you get that. Okay, and you leave x prime untouched. So you then have k x prime f of x prime e raised to power minus I k x. Okay, and so you also have a minus sign over here. Okay, right, and then of course you can switch the integration limits. You can swap the integration limits for the k prime integral and then relabel k prime as k. Okay, so you then have minus infinity to plus infinity dk over 2 pi minus infinity to infinity dx prime e raised to power ik x prime f of x prime e raised to minus ik x. Okay, this thing in the square brackets, you can identify this thing as your Fourier transform now. Okay, so you have f of k is then defined as minus infinity to infinity dx e raised to power ikx. Okay, so instead of in the Fourier transform, instead of having in the exponent e raised to power minus ikx as it was over here, some people put e raised to power plus ikx. Okay, but then of course for the inverse Fourier transform they have e raised to power minus ikx. Okay, so so it all balances out as long as the Fourier integral theorem is satisfied. Okay, you can redefine your integration variables. Okay, there is another convention as well which is quite common, is that you have this factor of 1 over 2 pi over here. Okay, what I have done above is that I have put in this factor of 1 over 2 pi all in the inverse Fourier transform when you go from capital F of k to f of x. So I've included the 1 over 2 pi factor with dk, not with dx. Okay, some people take a more symmetrical approach. Some people include some people write the Fourier integral theorem in this form. Okay, so the Fourier integral theorem, remember, is this thing. So they peel off this 1 over 2 pi into two parts. Okay, so you write 1 over 2 pi is equal to 1 over square root 2 pi and 1 over square root 2 pi. Okay, one of these factors they include in the Fourier transform, one of these factors they include in the inverse Fourier transform, so that both of these take a more symmetrical appearance. Okay, so they write this Fourier integral theorem as minus infinity to infinity dk over square root of 2 pi minus infinity to infinity dx prime over square root of 2 pi, and then you have e raised to power minus I k x prime f of x prime e raised to power I k x. Okay, so then they define this thing in the square brackets as a Fourier transform. Okay, the inverse Fourier transform then, instead of containing 1 over 2 pi, contains 1 over square root 2 pi. Okay, so there are different conventions. Okay, right, so you just have to be careful about which one you are following, and you have to be consistent throughout. Okay, the important thing is that the Fourier integral theorem has to be obeyed. Okay, as an example, consider the Gaussian function. So let me just write it down and explain what that means. So you have this thing, some constant, sigma is a constant, and you have e raised to power minus x square over 2 sigma square. So this is a function which, as you can see from the exponent, it's going to be peaked at x is equal to 0. Okay, and then for both positive x and negative x is going to fall off because of this x square term in the exponent. So it's going to look like essentially a bell curve. Okay, that's why your normal distribution is just a Gaussian. Okay, and this sigma is essentially representing the width of this function. Okay, so essentially the bigger the value of sigma, the bigger is this width. Okay, the smaller the value of sigma, the narrower it is. Okay, this factor in front is there to just ensure that this function is normalized, so that when you integrate it, the function over all values of x, you get 1. Okay, so first of all, let's check whether this condition is met, and we learn how to do Gaussian integrals along the way. So essentially, if you are going to integrate e raised to power minus x, you know how to do that, but how do you integrate e raised to power minus x square? Okay, that's what I mean when I say learn how to do Gaussian integrals. Okay, so first of all, let's look at integrals, this integral. Okay, right, so the first thing that you do, let me just do it in another form. Okay, let me do it in this form, x over a square. Okay, right, because that's closer in spirit to what we actually want to integrate. A is just a constant. So the first step that you do in doing this is that you first of all define x prime is equal to ax. Okay, no, x over a, that's what you want. Okay, so then this implies immediately that x is equal to ax prime. I'm doing this so that I get rid of this stupid constant in the denominator of the exponent. Okay, then I know from this that x square is going to be a square x prime square, right, and I also know that dx is going to be a dx prime. Okay, so let's just plug this in. When x is infinity, x prime is also infinity. When x is minus infinity, x prime is also minus infinity. So I'll get this integral as e raised to power minus a square x prime square divided by a square a dx prime. Okay, and then I can relabel this dummy integration variable x prime as back to x. Okay, so I'll get a times minus infinity to infinity e raised to power minus x square dx. Okay, right, now to do this integral, you say that this integral is equal to I. Okay, the trick now to do this integral is to write two copies of this integral. So to write I multiplied by I, so this is minus infinity to infinity e raised to power minus x square dx, and then minus infinity to infinity. Okay, I'll use some other variable to represent the dummy integration variable over here. Let's just use y. So you have this. Okay, and this thing is then given by minus infinity to infinity dx. I combine the two integrals as single double integral. Okay, so you have e raised to power dy, and then you have e raised to power minus x square plus y square, and that's what you have. I can do this integral now in polar coordinates. Okay, because this is easy to do in polar coordinates, because x square plus y square in polar coordinates is simply r square. Okay, so the trick is that we don't know how to do I, but we know how to do I square. Okay, and this represents integration over the whole two-dimensional xy plane, which in polar coordinates is, remember, is given by this thing, 0 to 2 pi d phi, and then you have r, and then this goes from 0 to infinity. Okay, so this is the little area element. R dr d phi is a little area element in polar coordinates. Dx dy is a little area element in rectangular coordinates. Of course, when you're integrating with the whole plane, those are the limits that you need to use in the your polar coordinates. So this I square is simply equal to 0 to infinity r dr, 0 to 2 pi d phi, and e raised to power minus x square plus y square simply becomes e raised to power minus r square. Okay, I can straight away do the phi integral. That gives me a factor of 2 pi, and I'm then left with 0 to infinity dr r e raised to power minus r square. And now I can do this integral because the derivative of r square is 2r. Some part of it was already there. Okay, so what I can do then is I can say, okay, that this has to be equal to 2 pi 0 to infinity, right, dr, and then I have minus 2r over here, but then I can do minus 2, minus 2 over here. Okay, so that you don't change anything overall, and that's what you have there. So you have actually just multiplied and divided by minus 2. Okay, so this gives you minus pi 0 to infinity dr, and then you have minus 2r e raised to power minus r square. Okay, and this thing is going to give you minus pi e raised to power minus r square from 0 to infinity, because the derivative of e raised to power minus r square is going to be equal to e raised to power minus r square times minus 2r. Okay, and this thing is then going to give you minus pi, and you're going to get, when you plug in infinity, you're going to get 0 because you get e raised to power minus infinity, and then you're getting minus e raised to power 0, which is minus 1, so you get pi. Okay, right, fine. Okay, so that's what you get for your for I square. Okay, so I square is given by pi. Okay, and so I is simply given by square root of pi. Okay, so now going back to our integral, this one, this is simply a times square root pi. So minus infinity to infinity e raised to power minus x square over a square dx is simply given by a square root pi. If of course I wrote this a square in the if of course I wrote this a square in the numerator, so this a square in the numerator, then I would be having square root pi divided by a. Okay, so this a won't appear over here, it will appear in the denominator. Okay, you can check that very easily. Okay, you just have to check this step over here, this rescaling step over here. Okay, so anyway, with that in mind, let's check. So we have over here, what we have to check is that given f of x is equal to 1 over square root 2 pi sigma square e raised to power minus x square over 2 sigma square, that the integral of this function over the whole real number line gives you 1. Okay, so you have 1 over square root 2 pi sigma square e raised to power minus x square over 2 sigma square dx. Okay, this square root of course goes outside, and you're left with minus x square 2 sigma square. Okay, right, and using the result that we have derived, this over here for our case a square is equal to 2 sigma square, right? So this implies that a of course is square root of 2 sigma. Okay, so then this we get 2 pi sigma square, and the result I get is square root of 2 sigma, and you get over here of course square root of pi, which of course gives you 1. Okay, so yes, the Gaussian function is normalized, and now let's calculate its Fourier transform. Okay, Okay, to calculate the Fourier transform, I just use the definition. I calculate the Fourier transform in this guys. So I have dx e raised to power I kx, and here you essentially just plug in f of x now. So this is 1 over 2 pi sigma square e raised to power minus x square over 2 sigma square. Okay, that's what I have, and then you can take this. So the convention I'm mostly following is that there's going to be e raised to minus I kx over here. Okay, so I'm going to take this thing outside. Okay, and I'll also have e raised to power minus x square over 2 sigma square plus I k x dx. Okay, fine. Now what I do to do this is that I complete the square over here. Okay, so essentially I have x square over 2 sigma square plus I k x. Okay, this thing is going to be given by 1 over 2 sigma square I take outside, so you have x square plus I 2 sigma square kx. Okay, and this thing then is 1 over 2 sigma square x square plus 2I sigma square kx, right, plus half of this thing, so you get I sigma square k, okay, whole square, right, and you then have to subtract, of course, 1 over 2 sigma square I sigma square k whole square. Okay, fine. And then we get that this thing is 1 over 2 sigma square x square plus 2 sorry, I can just combine this thing to 1 plus I sigma square k whole square. Okay, yes, that is reasonable, minus 1 over 2 sigma square, and I have I square is minus 1, I minus 4 k square. Okay, and this thing then gives me 1 over 2 sigma square x plus I sigma square k whole square, and then I have plus from here I have 1 over 2 sigma square k square. Okay, so that's what I have. That's what I can re-express this exponent as. The idea is that I want to write this term down as some variable whole squared, so then this whole thing becomes a Gauss integral yet again. Okay, so f of k then is given by 1 over square root 2 pi sigma square, and we have minus to infinity, and then we have e raised to power minus 1 over 2 sigma square x plus I sigma square k whole square. Okay, and we also have along with this e raised to minus sigma square k square over 2 dx. Okay, so I can pull this thing, of course, outside the integral because this does not depend on x. So I have square over 2, and you're then just left with this pesky integral that you have to do, x plus I sigma square k whole square divided by 2 sigma square dx. Okay, let me now define y is equal to x plus I sigma square k. Okay, and with this I immediately have that dy is equal to dx. Okay, and when y when x is plus infinity, y is plus infinity. When x is minus infinity, y is minus infinity. Okay, so essentially you have over here f of k is equal to 1 over square root 2 pi sigma square e raised to power minus sigma square k square over 2, and you then have minus infinity to infinity e raised to power minus y square over 2 sigma square dy. Okay, and this is one integral that we can do. So this is something that we just did. Okay, so you have over here square root of 2 pi sigma square is what you get. Okay, so this is 1 over square root of 2 pi sigma square e raised to power minus sigma square k square over 2 e raised to power minus, you get square root of 2 pi sigma square, so you get e raised to power minus sigma square k square over 2. So hopefully that gives you some idea of how to calculate a Fourier integral. One thing I would like to point out is that I wasn't very rigorous when I calculated the Fourier transform over here, in the sense that when I did this change of variables, I really should have changed limits of integration over here from minus infinity plus I sigma square k to plus infinity plus I sigma square k, and then you can actually do a contour integral to rigorously justify it. Result is correct, okay, but then you have to do actually contour integral to rigorously justify it, but that will lead us a little bit too much off course. If you're interested, you can easily Google it up how to do it rigorously. Okay, but just keep in mind, okay, that actually kind of fudged, okay, but at the back of mind I wasn't actually fudging. Okay, so anyway, the next thing to do, let's just have a look at what is the physical content behind this Fourier transform thing that we just did. Okay, so if you look at the original function is peaked at x is equal to 0. There is some spread to it. Okay, the spread is quantified by sigma. Okay, the bigger the value of sigma, the broader this peak. Okay, the Fourier transform, on the other hand, if you look at it, if you have a bigger value of sigma, like I just said, f of x has a broader peak. But if you have a bigger value of sigma, then the Fourier transform of the same function has a narrow peak. Okay, it's still a Gaussian. Okay, so Gaussian is actually a very special function in the sense that the Fourier transform of a Gaussian is also a Gaussian. In general, you don't have that. Okay, the Fourier transform of a function gives you usually a very different function. Okay, but the Fourier transform of a Gaussian is also a Gaussian. Okay, and if sigma is big, then the Fourier transform is narrowly peaked. Okay, while the original function has a broad peak. Okay, and vice versa. If the original function has a narrow peak, then the Fourier transform has a broad peak. Okay, this is in some sense is nothing but the Heisenberg uncertainty principle at play. Okay, remember in the wave picture of quantum mechanics, if you have a wave function, okay, which is narrowly peaked, that means that the position of the particle is well defined. When you take the Fourier transform of that by what we have just learned, the Fourier transform of that will not be narrowly peaked, that will be broad. Okay, so in other words, when the position is well defined, because the momentum of space wave function is a Fourier transform of the position wave function. Okay, when the position is well defined, the momentum wave function will not be localized. Okay, that will be spread out. So in other words, the momentum is not well defined so much. Okay, and vice versa. Okay, similarly, if you have a function which is well defined in time, essentially if you have a function which is localized in time, so if essentially you plot which is time, such a function, so it's mostly 0 and then it's localized, the Fourier transform of this essentially physically corresponds to how many frequencies do you need to add up, okay, with some weights to get this function. It turns out that, of course, if you have single frequency, then that's just a sinusoidal wave. Okay, and the sinusoidal wave is very different from this localized function. It turns out that you need to add in lots of different frequencies to get this function which is localized in time. Which again just means that the Fourier transform of this function, time dependent function, which will give you a function of frequency, the Fourier transform is going to be very broad because you need to add up lots of different frequencies. So the Fourier transform is going to be non-zero for many different values of omega, the frequency. Okay. Similarly, if the function of time is not localized, okay, so it's very broad, okay, then the opposite is true. Okay, so then you can get by with then your Fourier transform is very localized. You only need to add few frequencies. Okay, right? So that's essentially, so that's why this Fourier transform are essentially you have this correspondence, okay, from the original function to the Fourier transform function. Okay, when you change picture, that's what happens. Okay, now let me come back to the Fourier integral theorem. Okay, so I can write the Fourier integral theorem again as minus infinity to infinity dk over 2 pi minus infinity to infinity dx prime f of x prime e raised to power minus I k x prime e raised to power I k x. Okay, I can switch the order of integration, so I have minus infinity to infinity dx prime, okay, and then f of x prime, okay, because these two things because f is only a function of x prime, not of k, and then I can put the remaining integral like this, dk over 2 pi, and you have e raised to power I k x minus x prime. Okay, I now define this integral in the square brackets as the so-called Dirac delta function. So I define this as this thing, and I'll now investigate the properties of this integral. Okay, the Dirac delta function is extremely useful in many branches of science and engineering. Okay, you can write it down in many different ways. Okay, so it has some properties which we'll now investigate. Okay, but you can write down different forms of the Dirac delta function in the sense that you can write down the Dirac delta function as essentially in different ways. Okay, and all of those different ways satisfy those properties. This I've written down in one particular way, which is just an integral over some complex exponentials. Okay, but that's probably the easiest way because that's very clearly motivated from Fourier transforms. Okay, so essentially this is right now is just a definition. Okay, but now if with this definition, let's plug this definition back into the Fourier integral theorem. I have minus infinity to infinity dx prime f of x prime delta x minus x prime. Okay, the left hand side is just the value of the function at point x. The right hand side is the integration over all values of x, okay, multiplied by the delta function. Okay, this is very similar to this thing, that Vj is equal to sum over I Vi delta Ij. Okay, if you have a sum, within that sum there is a Kronecker delta, then the sum disappears, only a particular term in that sum remains. Okay, that's exactly what you have over here. You have the integral, which is a sum, okay, but it's a continuous sum. You have the function at all values of for all values along the real number line, but then this Dirac delta function only picks up the value of the function not at any value of x prime, but only at a particular value of x prime where x prime is equal to x, and so it throws out the value of the function at the point x. Okay, so that's why you have f of x on the left hand side. So that's why we call this the delta function, because this is very analogous to your Kronecker delta. Okay, so in a sense it's a continuous analog of your Kronecker delta. It picks out the value of the function at a particular point, okay, when it's under the integral sign. Let's investigate some other properties of this delta function. So first of all, from the definition, it should be obvious that this is an even function. Okay, right? So first of all, you can check that this thing is true. Okay, right? So all you need to do is to just define essentially k prime is equal to minus k, and you'll get that. Okay, so it's an even function, but more interestingly, if you try to evaluate delta of 0, okay, what do we get? Well, you get minus infinity dk over 2 pi, but since x minus x prime is 0, that's it. That's all you're getting, okay, because the exponent disappears. And this, of course, gives you 1 over 2 pi, and you get essentially infinity minus infinity, so you essentially get, well, loosely speaking, 2 times infinity, and this, of course, blows up, okay. So delta of 0 is essentially it blows up. On the other hand, let's now look for what does this thing that we have defined, this Dirac delta function, what does it look like for values for the case where x minus x prime is not equal to 0, or for the case where x is not equal to x prime. So to do that, we have essentially we go back to our definition. So I have minus infinity to infinity dk over 2 pi e raised to power I k x minus x prime. Okay. So I can start and doing this integral. What I would first do is that I chop up the complex exponential in two parts. So I have x minus x prime, right? And then of course I have plus I minus infinity to infinity dk over 2 pi sine of k x minus x prime. Okay. Here the integrand is odd. Okay, so that's an odd function with respect to k. So when you're integrating an odd function for minus infinity to plus infinity, you are guaranteed to get 0. Okay, so this whole thing goes away and you're just left with this integral. Okay. Right. Now, to find out the antiderivative of cosine, of course, is straightforward. The only tricky part over here are the limits. Okay. So rather than dealing with infinity and minus infinity as the limits, what I'll then do, what I do is that I'll define this as limit of, say, n goes to infinity. Okay. Of, I do this integral first. Okay. So first I do this integral for some arbitrary number n, okay, and then the lower limit is minus n, of course, and then I'll be taking the limit that n goes to infinity. Okay, so yeah, this is then equal to limit n goes to infinity, and one side you get 1 over 2 pi, and when you integrate with respect to k, you get 1 over x minus x prime in the denominator, and you get sine k x minus x prime, right? So you get minus n and n. Okay, that's what you have to plug in. So limit of, let me just put brackets over here, limit as n up to infinity 1 over 2 pi 1 over x minus x prime, and when you put n over here, you get sine of n multiplied by x minus x prime. Okay, and then when you put minus n, you get sine of minus n x minus x prime. Sine, remember, is odd, so you can take the minus sign within the argument outside, and you'll end up with 2 sine of n x minus x prime. Okay, that's what you have. Fine, and what I can do then is that I have over here, I can multiply and divide by n. So I have over here 1 over 2 pi, and then let's just forget about this 2 pi thing. Just let me just write down 1 over pi. These two cancels this 2. Okay, so I can then multiply and divide by n so that I get a more symmetrical appearance. So I have n, and then I have sine of n x minus x prime divided by n x minus x prime. Okay, and then of course I have and so that's essentially what I have. Okay, you can try plotting this thing for different values of n. So you can define a new function. Okay, so essentially you can define a new function of x minus x prime is given by, so this also depends on n, this is given by 1 over pi n sine of n x minus x prime n x minus x prime, and you essentially plot this series of functions, okay, this sequence of functions for different values of n. Say n is equal to 10, then n is equal to 20, n is equal to 50, n is equal to 100, and so on and so forth. Okay, so you have x minus x prime on the x-axis, okay, and then you have fn x minus x prime for different values of n. You'll see that as you increase n, okay, your function, this thing becomes more and more sharply peaked at x minus x prime equals to 0, and moreover the value of this function for very large n seems to be essentially 0 for the case where x minus x prime is not equal to 0. So essentially for very large value of n, this thing will become something like this, okay, so something like this, okay, so right, okay, you can try doing this on Mathematica or even a simple graphical calculator will suffice, okay, right. Which can also check that for any value of n, the area under the curve is always going to be equal to 1, okay, so let's check that. So essentially what I'm saying is that the dx minus infinity to infinity delta x minus x prime, this thing is then minus infinity to infinity dx, right, and delta x minus x prime is then given by limit n approaches infinity of 1 over pi n, okay, sine n x minus x prime divided by n x minus x prime, okay, fine. And now I can do a simple change of variable. Let me define y as n x minus x prime, okay, so then I have this immediately implies that dy is equal to n dx, okay, so I have then that, assuming that I can switch around the limit operation and the integral operation, then this thing gives me immediately limit as n approaches infinity of minus infinity dx, okay, and you have then 1 over pi, right, you then have n, okay, and you now change your dx to dy, so this thing becomes dy over n, okay, and you then have sine of y divided by y, okay, right. So this n and n cancel, and you're then left with the sign. So then essentially you don't even need to take the limit n approaches infinity. For any value of n you get the same area, and this thing will then be equal to minus infinity to infinity of dy over pi sine y over y. This integral we've already done, okay, when we did contour integration, okay, complex analysis. This is 1 over pi, and then you're left with this integral sine y over y dy. This integral, if you recall, is simply pi, okay, so you have 1 over pi times pi, which of course is just equal to 1. So the Dirac delta function has the property that the area under the curve is simply equal to 1, okay, and is sharply peaked. It's it just blows up. It's infinitely peaked at the point where x minus x prime is equal to 0, or where x is equal to x prime and is 0 everywhere else. So it's not really a function in ordinary sense of the word. No ordinary function behaves in this way. It's actually kind of a limit of a series of functions, of a limit of many different functions when you change some parameter within that. So that's exactly what I was doing over here. So essentially the Dirac delta function is essentially the limit of this different sequence of functions when you take n very big. Okay. So anyway, the Dirac delta function by itself is then not rigorously mathematically speaking is not really a function. It's it always has to you always have to make sure that the Dirac delta function by itself does not appear. It always should appear under an integral sign. Okay, then it makes sense. Okay, what you are doing. So for example, dx delta x minus x prime. Okay, f of x. This is just going to be f of x prime. Okay, so it samples the value of the function at a particular point. Okay, one way to see that would be, okay, that essentially this is 0 everywhere apart from the case where x is equal to x prime. Okay, so you might as well replace this whole integral by a single integral around the point x prime. Okay, and then the function, the Dirac delta function that just picks out the value of the function at that point. Okay, and now to prove any identity involving the Dirac delta function, you can proceed in two ways. So for example, consider the fact that delta x is minus infinity to infinity dk over 2 pi e raised by kx. Okay, so by the way, this integral just means that you are adding up a continuous set of sinusoidal functions, okay, to get a function which is totally localized at the point x is equal to 0. Okay, so that's what this integral is essentially implying. Okay, now you have this identity which says that for any constant a, this is true. So you can proceed in two ways. First of all, I can use this integral representation of the delta function that I've written down. So let's use that. That's one way to do it. This is going to be equal to by that representation. This thing is going to be 1 I k a x. Okay, and then I'm going to define k prime equal to a k, and then when k is, I'm assuming for the time being that a is positive. Okay, when k is plus infinity, k prime is plus infinity. When k is minus infinity, k prime is minus infinity. Okay, so you get minus infinity, you get dk prime over 2 pi, sorry, not dk prime over 2 pi, you get something different. You get dk prime, and then you have this factor of 1 by a which you can put out, and you have I k prime x. Okay, so this is just delta x. You have 1 by a delta x. Okay, you can now repeat the argument where a is negative, and you'll find that that delta ax is given by this thing. Okay, so you have to divide by the absolute value of a. Perhaps an easier way to see this is the following. So you have, if a is negative, then of course minus a is positive. Okay, that's a given. And if minus a is positive, then I can repeat the same argument over here, except that I'd have minus a over here, where minus a, remember, is positive. Okay, right, fine. and at the same time also have the fact that the delta function is an even function, so this must be equal to this thing. Okay, so looking at this thing where minus a, remember, is positive, a itself is negative, you can just combine this thing with this thing where a is positive to write the whole thing as a single equation which captures both cases, a being positive and a being negative. This is simply mod a and x. So this is an identity involving delta functions. There are some other examples as well. Okay. Another way to prove such an identity is as follows. So you essentially say that okay, the delta function really is useful for us only under an integral sign. So you have essentially delta ax. Okay. If I multiply this with some function f of x minus infinity infinity dx. Okay. This identity is implying the following, that this is going to be equal to 1 over a. For simplicity, I'll assume that a is positive. Okay, the extension to a being negative is very straightforward. This implies that you have minus infinity to infinity 1 over a delta x f of x dx. Okay, this is what this identity actually means in practice. That the delta function occurs under integral sign. You can replace this delta function with this delta function within the integral sign for any arbitrary function f of x. Okay, let's see if this is the case. For the left hand side, I can manipulate the left hand side as follows. So you have this thing. I can do a variable substitution. So essentially the key to proving all of these is to do some smart variable substitutions. So once you have this, then you have the dx is equal to dx prime divided by a, and so I can write this integral as minus infinity to infinity. A is positive if x is plus infinity, x prime is plus infinity, and so on. And so this is x prime f of x prime over a and dx prime over a. Okay. Now this thing is only non-zero when x prime is equal to 0. Okay, which means that this picks out this function when x prime is 0. Okay, if x prime is 0, then of course x prime over a is also 0. So this is then this 1 over a goes outside, so you're left with 1 over a and f0. Okay. On the other hand, coming back over here, the right hand side is equal to, you can take this 1 over a outside this integral and you're left with delta x f of x dx, which of course is just 1 by a f of 0. Good. Yeah, this identity is fine. Okay, because under the integral sign, the delta, both the left hand side and the right hand side produce the same thing. Okay, so much for the delta function. I'll now consider functions which are either even or odd, and I'll be considering Fourier transforms and the inverse Fourier transform of these functions. Okay. So for simplicity, I'll just do it for even functions. Okay, so I'll assume that that the function f of x is even. Okay, and you will see that in this case, you can simplify your Fourier transform and come up with the so-called the Fourier cosine transform. Okay, so essentially your transform, instead of involving a complex exponential, only contains a sine, a cosine. Sorry. Okay. So first of all, we start from the observation that if you have an even function, then the Fourier transform of this even function is also an even function. Okay, so let's see what happens there. So the Fourier transform is given by minus infinity to plus infinity dx f of x e raised to power minus I kx in the convention that I am following. And then you can write this as minus infinity to infinity dx f of x cosine of kx minus I sine kx Okay, and you can split up this integral into two parts, of course, and you have minus I 0 to minus infinity to infinity dx f of x sine kx. Now f of x is even. An even function multiplied by an even function is also an even function. An even function multiplied by an odd function is an odd function. An odd function multiplied by an odd function is an even function. Okay, these are all these things are very easy to prove. So this means that this is an even function. Cosine is also an even function. So this is an even function. Okay, this is an even function. This is an odd function. Even multiplied by odd function is an odd function. So the integral from minus infinity all the way to infinity will give you 0. So this goes away, and you're just left with minus infinity to infinity dx f of x cosine kx. Okay, I can simplify this further because the integrand is even. I can just write this as twice the integral from 0 to infinity. Okay, so that's the Fourier transform. I can also go and look at the inverse. Okay, so if I want to get f of x from f of k, remember I have to do this thing in the convention that I'm following. Okay, e raised to power I kx f of k. Okay, right. Okay, this can be simplified using the by seeing that this capital F of k is an even function, in the sense that capital F of minus k is equal to capital F of k. That's easy to show by looking at this thing. If you replace k by minus k, of course you get back exactly the same thing, since cosine of kx is equal to cosine of minus kx. So this capital F of k is an even function, and I'll play the same game, exactly the same game again. So you have 2 pi and e raised to pi kx. So sorry, yeah, capital F of k, and then capital F of k is an even function of k, and so only cosine survives, because sine is an odd function, and sine multiplied by odd function multiplied by capital F of k integral will give you 0. Okay, and then I can substitute for capital F of k from here. So I have 2 0 to infinity dx. Okay, fine, and you have f of x cosine of kx. Okay, so just so that there is no confusion, I should be putting a prime over here so I don't confuse this x with that dummy variable, and you have that. Okay, just as before, since this integrand is even, I can replace these limits from minus infinity to infinity as from 0 to infinity, but put in a factor of 2. Okay. This factor of 2 cancels this factor of 2, but there is an additional factor of 2 that comes up because I am now integrating from 0 to infinity. And so you have 2 over pi dk 0 to infinity dx prime f of x prime cosine of kx prime cosine of kx. Okay, this is essentially the Fourier integral theorem, specialized to the case where the function that we're looking at is an even function. Okay, this then motivates the definition of the Fourier cosine transform. Okay, so the Fourier cosine transform I can write as, the usual convention over here is to do it symmetrically. So this factor 2 over pi is chopped up into two equal parts. So you have square root of 2 over pi 0 to infinity dx f of x cosine kx, and then f of x is equal to 0 to infinity dk f c k cosine kx. Okay, you can see that these definitions are entirely consistent. If you just plug this f of c k over here, you just reproduce this thing. Okay, So that's how you come up with the Fourier cosine transform. You can do exactly a similar thing to define the Fourier sine transform. Okay, so these are, remember, these are just specialized versions of your Fourier transforms when you deal with an even function or odd function, which very often is the case because there's some symmetry in your system that you're looking at. So that simplifies your life. Okay. Okay. Just to now conclude this subject of Fourier transforms. Okay, in the next video I'll be moving on to Laplace transforms, but that will be a relatively shorter video because Laplace transforms share a lot of similarities with Fourier transforms. Okay. Let me just, the applications of Fourier transforms of course are many. They appear all over the place, but let's try to do one application which we are already kind of familiar with. I will try to use the Fourier transform to solve an ordering differential equation. Okay, the differential equation that we look at is this thing. This is a very standard differential equation, and this is equal to some arbitrary function of time. Okay, so I want to find this function y as a function of time, of course. For future convenience, I write the function on the right hand side, the non-homogeneous time, as minus g of t rather than simply as g of t. Okay, that will just make this minus sign will cancel number that minus signs along the way. G of t is just an arbitrary function. Okay. Now, the idea behind using the Fourier transform, or in fact any integral transform in solving such a differential equation, is that you Fourier transform the whole equation. The Fourier transform, if you look at the definition, is a linear operation. The Fourier transform of a sum of two functions is the sum of the Fourier transforms of the individual function. Okay, and so on and so forth. So it obeys all the properties of linearity essentially. Okay, so what we do over here is that you take the Fourier transform. So taking the Fourier transform I denote by the symbol L because it's a linear operation. Okay, I don't want to use capital F because I'm already using that widely for the Fourier transform. Okay, so essentially I'm saying that given this differential equation, I can write this thing. Okay, now this thing of course is a Fourier transform of y as a function of time. This will give me some function of frequency. Okay, because remember previously I'm using x and a, but usually if the independent variable is time, then the Fourier conjugate variable will be the frequency. So I'll write this thing as capital Y as function of omega. Okay, so that's that. This thing, of course, this minus sign, since the Fourier transform operation is linear, I can pull this minus sign outside. That is obvious from the integral definition of the Fourier transform. And you're left with the Fourier transform of g of t, which I denote as capital G of omega. Okay, what is left is this thing. Now there is a useful trick to doing this. Okay, so first of all, let me calculate the Fourier transform of dy by dt. Okay, by definition, the Fourier transform of dy by dt is essentially t. Okay, and you have e raised to power minus I omega t, and you have dy by dt. By definition, this is the Fourier transform of dy by dt. What you do is that you do integration to parts. So you push the derivative to the other term, e raised to power minus I omega t in this case. Okay, and you pick up a minus sign, plus you pick up some surface, the boundary terms. Okay, so you essentially have that this thing is equal to dt, and then you have d by dt of e raised to power minus I omega t times y. Okay, along with the minus, plus you have the boundary terms e raised to minus I omega t y from minus infinity. The usual assumption over here is that y is a function such that it decays at the boundaries. If that is the case, then of course y at infinity is 0 and y at minus infinity is also 0. So this term vanishes. Okay, right? Okay, this may not be the case. Okay, but then one of your assumptions is failing, so you have to be more careful then. Okay, Anyway, this thing then is minus infinity to infinity dt. You do this derivative, minus I gets pulled down, you have left with the exponential times y. Okay, so that's what you have. This is then further simplified as I omega you can pull outside, and you're left with dt e raised to minus I omega t y of t, of course. Okay, this thing is nothing but the Fourier transform of y. So this is capital Y omega. In other words, the Fourier transform of the first derivative of y is simply I omega times the Fourier transform of y. You can further generalize this result, and you can very easily show using something similar, using exactly the same integration by parts procedure, that the Fourier transform of the nth derivative will simply be I omega raised to power n times the Fourier transform of y. Okay, with this in hand, we then have, going back over here, we then know that this thing is going to be I omega square, I omega whole square, so that will give me minus omega square capital Y omega. Okay. Now you see the purpose of this minus sign, so that everywhere there is a minus sign, I can get rid of that stupid minus sign. Okay. The idea now is that you solve for capital Y of omega. So capital Y of omega is then given by capital G of omega divided by omega square plus 1. So you see, your problem, your original problem comes in terms of a differential equation. When you did the Fourier transform thing and all that, has now become an algebraic problem. Okay, so there are no derivatives over here. Okay, all you need to do is essentially just find of capital G of omega, okay, which you can do because you know your function g of t, and then you divide this by omega square plus 1 to find the Fourier transform of y of t. But usually what you want is y of t, so you have to take the inverse Fourier transform of this thing. Okay, now what you are doing over here is that you can define two functions. Okay, so you have two functions. One function is 1 over omega square plus 1. The other function, of course, is g of omega. Okay, so you have two Fourier transforms. Okay, so these are Fourier transform of some functions. Okay, capital G of omega is, of course, the Fourier transform of the function small g. Okay, so these two are both Fourier transform of some functions. These are two Fourier transforms multiplied together, and then I want to find out the inverse Fourier transforms of the product of these two Fourier transforms. What is that equal to? This leads us to the so-called convolution theorem for Fourier transforms. Okay, this just says that if given two Fourier transforms in general, the product of these two Fourier transforms is the Fourier transform of the convolution of the original functions. So f is the inverse Fourier transform of capital F, and small g is the inverse Fourier transform of capital G. Okay, so that's what the convolution theorem says. I'll explain what convolution is. Okay, the convolution is a process that occurs, it's just essentially a fancy overlap integral. It's a process that occurs often enough such that it's given a special symbol. It's just an asterisk on the line, okay, not in the superscript or subscript. Okay, it's very easy to prove this. So capital F of k by definition is minus infinity to infinity dx f of x e to minus I kx. G of k by definition is, I'll use some other symbol over here. So let me just write this as, now you just put the two together because you're forming the product, dx minus dy f of x g of y e to minus ik x plus y. Okay, to simplify this exponent, we define a new variable, say let's call that z. Okay, and I'll get rid of y. So this f of k, g of k, I can write as minus infinity plus infinity dx, and when y is in plus infinity, z is plus infinity. When y is minus infinity, z is minus infinity. So I get this. Then I have f of x, and I have g, and y, I have z minus x, and I have minus I k z. Okay, fine. So that's what I have over here, and then I can write this thing as minus infinity to infinity dz e raised to minus I k z, right? And then I have minus infinity to infinity dx f of x g z minus x. This thing in the square brackets is exactly what is defined as the convolution integral. Okay, so, and I leave it as an exercise for you to show. You just do a change of variables that this thing is also equal to this thing. Okay, so the convolution integral is just an overlap integral. So before I explain what that essentially means, let me just give you what do I give you some understanding of what do I mean by an overlap integral. So essentially an overlap integral, so for example, if you have two functions, one function is peaked over here, one function is peaked over here, this is f of x and this is g of x. Okay, and so if I form this integral, I know that I will get something very close to 0, because at points where f of x is non-negligible, this function g of x is very close to 0. At points where g of x is non-negligible, f of x is very close to 0. So this thing will give me 0. So this the multiplying the two functions together and then adding the product all up gives me some idea about how the two functions overlap. Okay. The convolution integral is very similar, except this is kind of a dynamic average. So in the sense that you allow one of these functions to slide, to move. That's exactly what this x minus z is doing over here. Okay, so essentially, this convolution integral, of course, depends on z. Okay, for different values of z, you will get different overlaps. That's why I called that this is this is a kind of dynamic overlap. Okay. Anyway, so once you have this convolution integral, so this thing in square brackets I denote as f star g, which just means that I'm taking the convolution. You are then, this integral is just taking the Fourier transform of this convolution. So that proves the convolution theorem. Okay. Now, if I look at this thing, I can take the inverse Fourier transform both sides. So that just means that the inverse Fourier transform of fk gk, the inverse Fourier transform of the product of any two Fourier transforms, is just given by the convolution integral. That's it. Okay, and that's what we were after. So here I have two Fourier transforms to find out, and these two multiplied together give me capital Y. I have to find out the inverse Fourier transform of capital Y. To find out the inverse Fourier transform of the product of these two things, I just form this convolution integral. Okay. So then I just have to write down the convolution integral. Okay, this convolution integral. I know small g because small g is just the inverse Fourier transform of capital G, and capital G, remember, by definition was the Fourier transform of small g. So the inverse Fourier transform of capital G will just be small g. Okay, which, remember, was the right hand side of my original differential equation. Okay, essentially. Okay, along with the minus sign. So then you have to find out this small f, which is inverse Fourier transform of this thing. Okay, so let's find out the inverse Fourier transform of this thing. So I know that capital F of omega is 1 over omega square plus 1. Then it follows that f of t is going to be given by minus infinity to infinity d omega over 2 pi e raised to power I omega t, and you have 1 over omega square plus 1. It's easy to do this integral using contour integration. I'll assume initially that t is positive. Okay, I need to deal with both cases because you are doing a convolution integral, okay, over different values of t. If t is positive, then first of all you note that this integrand, which is e raised to power I omega t over omega square plus 1, has poles at in the complex plane at omega is equal to I and omega is equal to minus I. Fine. And then you have to, if t is positive, you should be closing this contour in the upper half plane. Sorry, this is not so symmetrical, but okay. And you have the pole over here, another pole at minus I. Okay, so that's the contour using minus r to capital R. Take the limit where r goes to infinity. The contribution to the total contour integral along this arc is going to go to 0, because omega has a positive imaginary part. That I and this I combined together gives you a damped exponential part. So this is the limit where r goes to infinity. The contribution along this part of the contour is going to give you 0. You're left with this in contribution, which is exactly what you want to find. Okay, so that's why we're closing in the upper half plane. And then you use the residue theorem. There's only one pole over here. It's a simple pole, so f of t is simply given by 1 over 2 pi. Okay, and then you apply the residue theorem, 2 pi I times the residue at I. Okay, the residue at I is simply given by e raised to power I omega t, because you are dealing with simple pole, minus I, and then you have omega minus I, and you evaluate this whole thing at omega is equal to I. This thing cancels that thing, and you have e raised to power I t divided by 2y, okay, which is equal to e raised to power minus t over 2y. If on the other hand t was negative, you would be doing exactly the same thing, except that you would be closing the contour in the lower half plane. Okay, because then t is negative, so you want this thing to be a damped exponential, so you close the integral in the lower half plane, and then you're finding that the pole that you have to look at is at minus I. Okay, so you find a similar result. Combine them together and you'd find that f of t is given by essentially is essentially given by e raised to power minus absolute value of t, okay, fine, divided by 2i 1 over 2 pi I. Okay, so this absolute value just allows me to combine both cases into one equation. 2 pi cancels, I cancels, so this is just half of e raised to minus mod t. Okay, that's what I have. So finally I just form a convolution of these two functions, small f and small g, so that my small y, which is what I was after, is simply given by half of e raised to minus t minus tau. Okay, and you have g of tau. That's it. And this integral allows me to find out y for any small g. Okay, that's your solution to your differential equation. If you look at this solution, there's something fishy. Where are the constants? Remember, you're dealing with a linear second order differential equation. Let's go back what we were doing. Some place back. This equation. So this is a nice linear second order differential equation. You need to have the solution as a sum of two solutions. Remember, the complementary solution and the particular integral. Okay, what you have found is essentially the particular integral, because this thing contains no constants whatsoever. Okay, what happened to the complementary solution? Well, the complementary solution, if you go back, the differential equation is this. And if you want to find the complementary solution, you just set the right hand side equal to 0. The solution to this equation, of course, is that you're differentiating some function twice, you're getting back the same function. So then the complementary solution is, of course, just this thing, exponentials. Okay. Now the point over here is that these solutions won't be captured by this Fourier transform method, because remember, I was assuming when I did the Fourier transform of the equation, I was implicitly assuming that the Fourier transforms exist. Okay, when I did this Fourier transform of the equation, for some functions, for quite a lot of functions actually, the Fourier transform may not exist. Okay, because remember, the Fourier transform is given by f of k minus infinity to infinity dx, and you have e raised to minus ikx f of x. This thing is not a damped function, this is an oscillatory function. So if this thing actually blows up, because this integral goes away all the way from minus infinity to plus infinity, if this thing blows up, then the whole thing is likely to blow up. And that's exactly what's happening over here. This thing blows up for positive values of t, this thing blows up for negative values of t. That's why the Fourier transform does not exist. Okay. But anyway, we have uncovered a pretty powerful way of finding out the solution to differential equation. At least for particular integrals you can easily do it. Okay, for many differential equations. Okay, for it turns out that for partial differential equations the technique of Fourier transforms is indispensable. But for ordinary differential equations, when you're dealing with initial value problems, so you're given the value of the function at time 0, the value of the derivative at time 0, okay, it's usually much easier to use a similar transform to the Fourier transform, which is called the Laplace transform, which I'll explain in the next video. The idea is simply that, okay, sometimes the Fourier transform is not well defined because this thing is oscillating. Okay, what happens if you make this damped? So instead of e raised to the minus ikx, I set k to be purely imaginary. Okay, so that essentially I'm getting something like e raised to the minus kx f of x, something like this. This is not the Laplace transform, but it's something similar to the Laplace transform. Then I can expect that for a much broader range of functions the Laplace transform will exist. Okay, and then we can probably be able to find or the full solution to your differential equation. Okay, so next video, Laplace transform. Okay.